In this video, you will learn about text as data applications. So this is the third step in our text as data recipe. We need to learn some methods that we can use to solve our text as data problems. So you will learn about 3 applications. The first one is training a logistic model to classify whether text is positive or negative. The second one is using lexicons to analyze text data and specify whether a text has a positive or negative sentiment. And the third one is topic modeling, where we will use unsupervised machine learning to categorize our text into topics. So let's get started with that. First, training a logistic model for text classification. So we called the structure of our movie review data set. First, we had a variable containing the reviews, which is called review. Then we had a variable stating whether the person had a positive or negative sentiment towards the movie. That is called sentiment. And then we had a variable stating whether the review is in the test or train set. So you can see the data set here. And you can see that for example, the first review has a positive sentiment. So the one is positive sentiment. That means that we have labeled each review with a sentiment. And what is useful here is that we can train a machine learning model to on our train reviews, so our reviews that are in the train set, and we can use that to predict the sentiment of our test reviews. So the goal is to predict the sentiment, if it's positive or negative, of the reviews just by inputting the words in the reviews. So we might not know the sentiment of the text beforehand, but by training this machine learning algorithm, we can use it to predict whether it is positive or negative, the text. And the machine learning algorithm we will use is a logistic regression model, which is good for this text classification problem. So how do we do this in practice? First, we need to load the train and test dataset into 2 different datasets. So remember that we have already cleaned the data with our cleaner function beforehand. But if you haven't done that, then you should do that before you move any further. Okay, so here first we split our dataset into a train dataset and a test dataset, and then we randomly sort our datasets. So we mix positive and negative reviews. And in the end here, we take out the predictor variable, which is the reviews. So we call it X. And we also take out what we want to predict, which is the sentiment, and we call that Y. And we do that for both the train and the test dataset. So second, we need to make our bag of words, and we also want to downweight the common and rare words, and we do that with the TF-IDF, which you have learned how to use. So remember we used the count vectorizer class. Oh, sorry. Remember we used the count vectorizer class and the GF-IDF transformer to do this. You can also use the GF-IDF vectorizer, which combines the two classes here. So we will use the GF-IDF vectorizer now. So we import that class first, and we store it in GF-IDF to ease coding. And then we make our bag of words with this fit transform function. So it looks very similar to what we had done before. And we do that for the train set and the reviews in the train set. Third, we're now ready to fit our logistic regression model on the train set sets back of words, so what we call xtrain back, and fit it on the true sentiments, which was the Y train. So first we import the logistic regression class from the scikit-learn library, and we will install that logistic regression model in LR, and then we fit the model with the bag of words from the train set and the sentiments from the train set. So when we have done that, we can now test our fitted logistic regression model on both the train set and the test set, and see how well does it actually perform in predicting whether the sentiment of the review was negative or positive. So remember that the only input this algorithm gets is the bag of words that we computed from the reviews. So that is our structured way of representing the reviews, which we can use in this machine learning algorithm. So remember that we need a structured way to represent our unstructured raw text, and we always need that. So that is so let us test our model now. So to test our model, first we need to also make a bag of words, which is also GF-IDF transformed for the test set as well. And for this we use the transform method. So remember not to use the fit transform method as in the train set, because we will only use the words from the train set to fit our model up. So there might be more words in the test set that we don't see in the train set, but we will not use those. So use the transform method. And then we can predict the sentiment, and we do that with the predict method of the logistic regression. And we store that in train preds and test preds. And we can then compare the predicted sentiments with the actual sentiments. So what I print here is the share of reviews where we actually predicted the right sentiment with our logistic regression model. So what we can see is that for the training set, we predict the right sentiment in 93% of the time, and for the testing test reviews data set, we predict the right sentiment 88% of the time. So it makes sense that we don't have as much accuracy in the test reviews, because we fitted the model on the train reviews. Yes. Another nice little feature with this logistic regression model is that we can use the coefficients that it computes from this model to say something about the importance of each word. So I will show you how to do that. Okay, here first we just save all the words, all the features, we can also call them that, and we do that by getting the features of the words with this method here, and saving them in a list called features. Then we get all the coefficients of the features, and we do that by typing .coef underscore and save them in coefficients, and then we show them here in the coefficients of each feature or word here in this data frame. So we can see that it stores all the words that we have in our model and the coefficients they have. So you can see that we have more than 100,000 words, different words in our model and in our backup words. So it's a lot of features. Okay, here if we try to print the 20 words with highest positive sentiment, so that means the words with the highest coefficients in our model, we can then see which words that is, and that is words like great, excellent, best, perfect, wonderful, love, fun. So it really makes a lot of sense that these are the words that are most important for predicting positive sentiment. So contrarily, if we show the 20 words with the lowest positive sentiment, so that means the words with the lowest coefficients, we see words like worst, bad, awful, waste, boring, poor, and so on. So it also makes a lot of sense that these are the words that predicts negative sentiments. All right. Now to the second application, which is lexicons. So we have just seen what we can do when we have labeled data. Then we can fit a machine learning, supervised machine learning algorithm to actually predict, for example, sentiments in text. But sometimes we don't have these labels in beforehand. Sometimes we don't have the sentiments of each review in our data sets. So yeah, for example, for our review data set, it means that we don't know in advance whether the review has a positive or negative sentiment towards the movie. And if we don't know that, we cannot train a machine learning model to classify the sentiment. So what can we do instead? we can use these predefined lexicons. So what these lexicons do is that they have a dictionary of words that can have some predefined labels. For example, the words have a polarity score, which is positive, negative, neutral sentiment. They can also have a label defining mood and also intensity of the word, the strength of the word, and so on. So we can use these predefined labels to score the sentiment of texts. And the more positive words in the text, the more positive will the sentiment be of the text combined. So the more positive words we find from the dictionary up here in the text, the more positive the sentiment will be. And in contrast, the more negative words in the text, the more negative the sentiment will be. So you can read more about lexicons on this link, and if you would like to work with this, I encourage you to read this article. So there are a lot of different lexicons. I will just focus on two. The first one is Afin, which is actually a Danish lexicon, and it is one of the oldest and also quite popular and also very simple lexicon. So another one is Veda, which is a little bit more advanced, and you can read about it in these two links. But I will also talk a little bit about them. First, Afin. So Afin is a Danish lexicon, and it is very simple and quite popular because it's one of the oldest, and it is word list based. So what it simply does is that it contains more than 3,000 words that are scored for polarity. So then it compare the words in a text that we want to score the sentiment on. It compare the words from this text with these more than 3,000 words. And in the end, it provides us with a polarity score. And if we get a positive score, then it means that it is a positive sentiment. And if we get a negative score, it means that it is a negative sentiment that this lexicon predicts in the text. So Veda, it is specifically tuned to social media. So if you use text from social media, then Veda is a good lexicon to use. And what Veda does is that it both scores on polarity and also intensity of emotions. And it is both word list based as Afin, but it is also rule based, which means that, for example, it knows that did not love is negative because of the negation not. And Afin actually doesn't look for something like this. So Veda is a bit more smart here. So in the end, it compare all the words in the text with the Veda dictionary. And if you get a positive score, yeah, then it predicts a positive sentiment. And if you get a negative score, then it predicts a negative sentiment in the text. So how does it work in practice? In practice, the document is tokenized, so you know how to do that already. And for each token in the document, it is matched with the words in the lexicon. So each token we look at, is it positive, negative, or neutral, as stated in the lexicon. So when all the token sentiments scores are found in the document, they are summed or averaged, and then we predict an overall sentiment of the document by this sum or average score. And we can see how we can do it in Python, first with affin. So first we import the affin package, and we use this function affin, where we allow for emoticons in the lexicon as well. And here I have just chosen some random sample of reviews. And for each review, I then print the text of the review and the actual sentiment, and then also the affin score. So here's the text of the review, the first review. The actual sentiment is positive, and the affin score actually predicts that the sentiment of the text is negative. So it wasn't right here. So if we look at the next review, we see that that is also positive, and the affin package actually also predicts that. And the last review we see is negative, and we also see that the affin package actually predicts that. So we can use the affin function and the lexicon to predict the sentiment of all the reviews we have. So it would take a while to run this code, but I've done it already. So what we do is that we just iterate through all the reviews we have, and then find the score of the review, and then list the score in as a negative sentiment or as a positive sentiment, defined by this threshold 0. So, and here I then find the share of correct sentiment scores in the data set. So we can see that in 71% of the times, the affin lexicon actually finds the right sentiment in our review. So it's not as high as our logistic regression model, but if we don't have any labeled data, then it might be our only possibility. So we can do the same for Veda. And with Veda, we import the sentiment intensity analyzer class, and we also download the Veda lexicon. And we can then use this class to compute the polarity score as well, in the same way as in affin. So we iterate through these sample reviews, and we print the review text and the actual sentiment and the Veda sentiment that it predicts. So the predicted sentiment is a bit different from the affin sentiment. Here we actually get a score for each possibility in the Veda library. So we get a score for a negative, a neutral, positive sentiment, and then we also get the compound score. So this is the compound score is what we really look for, and if this is positive, then it's a positive sentiment. If it's negative, then Veda predicts a negative sentiment. So here, the first review, it predicts a positive sentiment. And so that is actually correct. Before, Finn actually predicted wrongly. Here in the second sentiment, it also predicts a positive sentiment, and that is also correct. And in the third review, it predicts a negative sentiment, and that is also the actual sentiment. So we can see how data actually performs when we predict sentiments for all the reviews. We do that in the same way as the Finn lexicon. And what we get is actually a bit smaller share of correct sentiment scores than the Finn library. And there may be a lot of explanations for that. So I don't know the exact explanation for why there is a difference. But that may differ from each type of text that you are working on. For example, if we had social media data, for example, Twitter text data, then Veda may be better than Finn. Okay, now to the last application in our text data application, which is topic modeling. So topic modeling is the task of assigning topics to unlabeled text documents. So in our movie review example, we can assign the movies into movie genres only based on the review. So what we do is we cluster all the reviews that contain similar words. For example, reviews that contain words like horror, scared, shock, blood. They may be clustered into the same topic, which might be horror movies. And we do this only using an unsupervised machine learning algorithm, which is called latent Dirichlet allocation, also LDA. And what this algorithm does is that it finds groups of words that appear frequently together across a lot of documents. So the groups of words that appear frequently together will then be our topics. And this is done without us as a human supervising which words will be in which groups. So this is only done by the algorithm, and you will see that it actually does quite a good job anyway, even though we are not specifying any topics beforehand. So how does it work in practice? As an input, this LDA algorithm takes a bag of words model, as you have worked with a lot now. And it then outputs two things. First, it outputs a document to topic matrix. So it allocates each document to a topic. And it also outputs a word to topic matrix. So it also allocates each word to a topic. And one thing that is important is that we need to remember that it is us that define the number of topics beforehand. So you can say that the number of topics is a hyperparameter. And because we don't know how many topics there are actually in these reviews, this is a bit arbitrary, but we can try to play around with it and define different number of topics. So we can try to tune this hyperparameter and see what is actually the best number of topics to have that catches the most clear topics. So you will see that in a minute. How does it work in Python? First, we need to make our bag of words. So here we do it in a little different way than you have seen before. So first, for convenience, we use the built-in stop word library in scikit-learn to remove all the stop words. And then we set the maximum document frequency to 10%. So a word must not be more than 10% in more than 10% of the documents. So we exclude the very common words. And we also limit the number of words to 5,000 most frequently occurring words. So we also exclude the words that are not that frequent. And we do that to limit the dimensionality of the dataset, so we can actually compute the LDA allocation. So this maximum document frequency and the number of words are also hyperparameters that you can tune. So you can play around with it and set the 10% and the 5,000 to other numbers and see if it works better. So here in the bottom, you see our code. First, we import the count vectorizer from before, and then we set our parameters in here, and we make our bag of words in the last line. So with this bag of words, we can now fit our LDA estimator to this bag of words. And we specify the number of topics to be 10. You can try to specify another number. And because it needs to go through 50,000 reviews to compare all the words that seem similar, this code may take a while. So it may take up to 5 to 10 minutes on a normal computer. So how we do it is that we import the latent dirichlet allocation, and we store that in the LDA variable here, and then we use the function fit transform and input our bag of words to get our review topics. So our topic modeling can actually be done in very few lines of code. Okay, so now we have our topics, 10 topics, and now let's print the 5 most important words for each topic. So how we do that is that we get our words from the get feature names out method, and we store that in word names. And then for each topic and topic index in this LDA component, which stores a matrix containing the word importance for each topic, we get the first 5 most important words in each topic. and we print those words. So first we print the topic number, then we print the 5 most important words, and we do that by sorting the words with so we get the most important words first, and we do that like this. So what we get is these topics and these words. So you can go through them and try to see which topics the algorithm actually finds in these words. So I have done that, and you might, if you go through these 5 most important words, you might identify the following topics. So the first topic might be action comedy movies, the second might be musicals, and the third war movies, and the fourth is maybe not a movie genre, but it is reviews somehow related to the quality of acting. You can see that from here. So it's the words are role and performance and place and actor. So the fifth may be movies from home, and fiction movies and horror movies, and eighth are bad movies. It might be. You can see the words are worst and awful and boring. And the 9th topic is feel good or family movies, and the 10th are is movies related to series. So our topic modeling algorithm somehow did a good job placing the reviews into topics, but there is one con in this topic modeling, is that you actually need to define the name of the topic yourself. So that is that can be different from person to person, what you actually define the topic as.